Today we have lecture number 16 of the course ME314 Fluid Mechanics 2, and this is the first lecture of this week. Earlier we already have started with potential flow, and we have worked out what is velocity potential function. Today we will go into the basic potential flows, and the lecture content is we will derive expression for stream function and velocity potential function for a uniform flow, and then we will go into the source and the sink flow, and then we will go into the vortex flow, and obviously these stream function and velocity potential functions for these basic flows to be worked out. Okay, let's start with uniform flow. So uniform flow is you can think of in which the fluid is flowing in such a manner that the magnitude of the velocity is constant, and it is following certain particular direction. So we can think of when you have streamlines in such a manner they are all straight and parallel, and their magnitude is not changing as you are moving in the space. We can think of just arbitrary streamlines. So psi1 is the first streamline, psi2 is mathematical function representing another streamline, and so on. And phi1, phi2 are those perpendicular lines to those streamlines which are velocity potential lines. At this point, we assume that the magnitude of the velocity is in the space x and y is constant, and the velocity which is the constant velocity, or we call it u infinity, is the magnitude of that velocity that makes an angle of alpha with the horizontal axis or x-axis. So this magnitude remains same. That would be the representation of the uniform flow. And if you have to work out the component of the velocity, so if u infinity is this vector, then horizontal component would be u infinity times cos of alpha, and vertical component y component would be u infinity times sine alpha. So sine alpha will be this vertical component, and this horizontal component is u infinity cos alpha, and with the sine Cartesian coordinate system in 2 dimension, this horizontal component is u component and the vertical component is in the y direction, that is the v component. Let's say we have the velocity component, so we know the velocity field, and next is to work out their corresponding stream functions. And we know from the definition of the stream function that if you know the stream function and you differentiate with respect to y, you are going to get the u component of the velocity. Similarly, if you know that stream function, if you differentiate it with respect to x, you are going to get the negative v component of the velocity. Similarly, we can have an expression for velocity potential functions. Another way to work out their component of the velocity, if you know the velocity potential function phi differentiated with respect to x to get the u component, differentiated phi with respect to y to get the y component of the velocity. Okay, let's take it the stream function for this. U is how the psi changes with respect to y, and for this uniform flow we know the value of u is u infinity times cos alpha. So which is already I know that, so I am interested in calculating the corresponding stream function. So I have to take the variable psi on the left hand side and y on the other side. So I have separated the variable and integrated it. So psi would be u times y plus some constant. Since we are varying with y, so the constant would be some function of x, because here independent variable is y. So here whatever the constant of integration would be some function of x. So I know the stream function just by integrating it. So I mean it is true everywhere. Whenever you know stream function, by differentiation you get the velocity component. So if you know the velocity component, you have to integrate to get your stream function. Same is true with the velocity potential function. If you know the velocity and you have to work out, you have to integrate. If you know the velocity potential functions, you differentiate to get the velocity component. So this is something we know this stream function, okay, but we do not have an idea about what this integration constant is. But as we know, we have one more information that the velocity component in y is also given. So I have to differentiate this stream function with respect to x to get the velocity component of y. So the next step is to differentiate psi with respect to x. So my independent variable here is x. So whatever is y or any constant something multiplier would be 0 here. Its derivative would be 0 because I am differentiating with respect to x. And this constant would be some function of x. So if I differentiate, it would be its first derivative that I used with f prime x as a first derivative of this expression. So from this step to this step we have integrated. From this step to this step we have differentiated with respect to x. Here we have integrated with respect to y. Okay, so as I know dou psi by dou x is nothing minus v, I just substituted here the minus v, and I have an expression of the first derivative of x would be negative v. So I have the first derivative of x that would be the negative v, and negative v is something known to me. So if I first derivative would be this, then the function would be some function of x. So here what I have done is derivative of f of x is actually negative v. So derivative of f of x, then variable is separated. Here you have x, so you integrated. So this after integration, this first derivative would be some function of f of x, and if you integrate v with respect to x, it would be minus v x. So here what I have done is substitute back because I have the information about, obviously there would be some constant of integration here, but I've just taken it 0 here. So I have the expression for f of x, and I have substituted back f of x again to this because the variable, whatever the variable is, that is minus vx. So my expression for stream function would be u times y plus some function of x, and some function of x here is minus vx. So in this way I would be able to work out the expression for my stream function. I just substitute the local component of u in terms of u infinity cos alpha. So v would be u infinity sin alpha. So here u infinity is common, I can take out common here. So this would be the stream function if you have a flow, uniform flow, having u infinity is the uniform velocity, and the whole flow is such that the streamlines are parallel to each other and they are moving in one direction, or that direction is represented by the angle alpha, which makes with the horizontal. The next is to work out its corresponding velocity potential function. So as I know the velocity components are known, I have to work out the velocity potential function. So phi would be the same procedure, just integrated to get some function of x. Since I am integrating with respect to x here, so the constant would be some function of y. And as I know, the next step would be to similar manner differentiate phi with respect to y. So that would be the first derivative of that function, and that would be dou phi over dou y, and dou phi over dou y is equals to the v component of the velocity. So it is the first derivative of y is v. So the function of y would be some function v times y. So after integration you got this. So you substituted f of y back into this expression to get the velocity, to get the corresponding stream function. So I have a stream function phi u times x plus some function of y, and some function of y is v times y. Now we can substitute the local u and v into the expression of velocity potential function. So I just substituted u is u infinity times cos alpha and v is u infinity times sin alpha. Here u infinity is common, so I can take it out common. So these two expressions would be the expressions for corresponding stream functions and velocity potential functions for uniform flow case. We could have the simplified version of this because here all the streamlines or the velocity magnitude of the velocity is constant and the streamlines are parallel to each other and moving in certain one direction. So let's say if we are moving in x direction, then alpha would be 0. So if I take alpha to be 0, so eventually alpha is 0, it means cos of 0 is 1 and sine of 0 is 0. So my stream function would be simpler, u infinity times y. And similarly, if I put cos of 0 here, alpha 0, cos of 0 would be 1. So it would be some u infinity times x, and sine of 0 is 0. So you have simpler expressions for stream functions. So that would be the representing at given y, let's say y here is y1. So corresponding to y1 multiplied by u infinity, there is some stream function. Similarly, when y is y2, you have another stream function. When y is y3, you have another stream function. And vice versa, we can work out the velocity potential function, which will be orthogonal to the stream function. So at some value of x, which is x1, you have corresponding velocity potential function would be phi1. When x is x2, you have a corresponding velocity function would be phi2. So in this way, you will be able to draw the flow net for this uniform flow case. Okay, the next type of basic flow is, we call it a source flow and sink flow. So in uniform flow, you have lines which are purely either horizontal or make some angle. But in source flow or sink flow, the velocity having only the component that is an acting component is the radial flow component. So there is no tangential component present. So if you have a velocity and think of velocity in a polar coordinate system, so instead of x and y, you have r and theta. So r would be the direction which is the radial direction, and theta would be the direction perpendicular to the radial direction. So if your flow is such where there is only acting component is in the radial direction and the tangential component is 0, then such a flow is called source flow. Source when it is outward and sink when it is inward. So the source and sink would be just the change of the direction. Okay, how to get their corresponding velocity components and their corresponding stream functions and velocity potential functions. Okay, we just suppose that, let's say, out of the paper in the z-axis, you have a sort of a thin pipe manifold and some water is coming out, and when this water is coming out, it goes directly into the radial direction. There is no other direction for the flow. Obviously is a hypothetical situation. So fluid coming from the source, that is an origin, when x is 0, y is 0, or you have theta 0 and r 0, and then the fluid comes out in the radial direction, and the tangential, there is no flow in the tangential direction. Just assume that the flow coming out from this pipe manifold whose length is b and whose volume flow rate is q. So at any radius r, we can calculate its volume flow rate. So volume flow rate would be Vr is the speed. So as you know, you just multiply area with the velocity to get the volume flow rate. So 2 pi rb would be the two dimensions. R is in meters, b is in meters, so it would be meter square. So that would be an area, and if you multiply area with this velocity, you will be able to get the volume flow rate. So here in this case, at any radius r, the flow rate would be 2 pi rb and times the velocity in the radial direction. We can write Vr on the left hand side and the other thing on the right hand side, and we know the volume flow rate and the width of the manifold pipe from which the fluid is coming out in and that is placed in the z direction, and the fluid comes out once it come out from the pipe, it goes only in the radial direction. So here you have the relationship between the radial component of the velocity, which is a function of r, because q is constant, b is fixed, 2 pi is fixed. We just make this q over 2 pi be some constant with another letter called m, and m here, so our expression for velocity component in the radial direction would be m over r. And keep in mind that this velocity is only defined when r is not 0, because when r is 0, obviously at this point the velocity is not defined, or it would be r0, it means the velocity would be very high, infinity. So the relationship between what you call it a source, if this constant m, fluid is coming out from this pipe, m is positive, then it is called a source flow. Otherwise what will happen is we can think the flow is coming in the radial direction and it is something going into the pipe. So in this case m would be negative, and that flow would be called as sink flow. So the source in sink is just the direction of the radial component of the velocity. So when radial component of velocity is in outward, it would be called as source flow, and when it is inward, it would be called as sink flow. So the expression for magnitude of relative velocity would be the same. Only difference would be the sign of m is going to change. And here m is called the strength of the source or the sink. As we know, the source flow and sink flow is a particular class of flow in which there is an only active component is in the radial direction. Their tangential component is 0. And as we know, the relationship between calculating stream functions and velocity potential functions in polar coordinate system. So this would be the radial component of the velocity, this would be the tangential component of the velocity, and these are the expressions if you have a knowledge of stream function, or if you have a knowledge of velocity potential functions, you can work out their components. So the same we have done it for uniform flow, the same procedure we adopt. We just pick it one radial component of the velocity and just put it as we know the radial component of velocity is m over r. So r and r here cancel out and make it dava psi by dava theta would be just m. So separating the variable, psi would be m times of theta, and at this place I have assumed that the concept of integration is assume 0 here. So dava psi by dava theta would be m here, so psi would be some function of m times theta. So at every theta you have a corresponding psi. When theta is 0 radian, your psi is 0. When theta is, let's say 30 degree or pi by 4, when it is 45 degree, then m times pi by 4 would be corresponding stream function, and so on. So these psi lines would be your radial lines where flow is coming out. So that because the dominant direction flow is in the radial direction, so these family of lines at every theta is going to represent the family of streamlines. And we can write in terms of the Cartesian coordinate system, because as I know in polar coordinates, x is r cos theta, y is r sin theta. So when you divide these two equations, r and r, then you get tangent inverse of y by x. Okay, so similarly we can work out the velocity potential function, because Vr is dava phi by dava r, and we have a knowledge of m over r. We know that v theta is 0, so that is not useful at all. So m over r is the radial component. So here what I need is to separate the variables and bringing it 1 over r, and the integral of as the derivative of log of r is 1 over r, then the integral of 1 over r would be ln r. So once I have integrated, I got this function m times ln r, and that would be representing concentric circles, because you know the equation of circle is x square plus y square equals to r square if its center is at origin. So just substituted back the value of r in Cartesian coordinate system, so you have an expression for corresponding velocity potential function. So if you have a knowledge of the velocity components, you can easily work out its corresponding stream functions and the velocity potential functions. These two are in polar coordinates and these two are in Cartesian coordinate system, and we can plot it. The flow is in the radial direction, so the blue lines are representing the streamlines, whereas the concentric circles are representing the velocity potential lines or equipotential lines. So that is represented, stream functions are represented by m times of theta, because every theta there is corresponding stream function. And similarly for these concentric circles are represented by this equation m times ln r x square plus y square, which is an equation of circle. So every circle is phi 1, phi 2 and phi 3 and so on, and the velocity in the radial direction is m over r, as we already know. So this is the flow, basic flow. We call it a source and sink flow. Okay, there is another type of flow. For example, in a source and sink flow, we have the streamlines are in the radial direction. So in vertex flow, the things are opposite. So the radial component is an absent component, and the only acting component that is in the tangential direction. So streamlines would be your concentric circles, and the radial lines would be your equipotential lines or velocity potential lines. So you can think of vortex flow to be opposite case of their source and sink flow. So here we have vertex flows is actually such a flow in which your streamlines are concentric circles. In radial flow, your streamlines are in the radial direction. Your equipotential lines were concentric circles. Here you have an opposite situation when your streamlines are concentric circles, so it means the only acting component is in the tangential direction. So the velocity in the radial direction is considered to be 0. So, and that obviously the magnitude of the tangential component would be some function of r, and that is something we will be able to work out. And we will see. Okay, in reality, there are so many situations which are considered as vertex flow, like tornadoes, not exactly vertex flow, but sort of a spiral flow. We will see it later. The flow that has been taking place at the tip of an aerofoil. So this is an aerofoil, this wing, and on the tip, this is the circles, vertices are there present. That is actually close to vortex flow, and you can see the flow in the drain hole. Can we think of the acting component is actually the concentric circles now. So can be approximated, not exactly, but can be approximated. Okay, vertex flows, actually there are two categories, rotational and irrotational. Since we are talking about potential flow, one of the condition is flow must be irrotational. So that would not be potential flow if it is rotational. So we will talk in the end about rotational, but our focus would be on irrotational vortex flows. Okay, so as you know, for irrotational case, your vorticity must be 0 or circulation across the streamline must be 0 for an irrotational flow. That is the condition for, or curl of the velocity should be 0 for any irrotational flow. Okay, just think of a flow in which you have streamlines are concentric circles. So you have one of the streamlines psi, and then you have a neighboring streamline psi plus d psi. Okay, you just take a closed path A, B, C, D, and you know, if you know R, and your velocity is in the tangential direction, and if you travel certain distance dr in the radial direction, your velocity would be v theta plus some change in that velocity as you move in the radial direction. So we just calculate here the circulation for this contour A, B, C, D. So A, B, there is no component of velocity, so the velocity is 0. And for BC, because I am calculating an anti-clockwise direction circulation, So my velocity is in the opposite, so that's why I put a negative sign here. So v theta plus dv theta would be some velocity component, and this arc length would be r plus dr is this distance multiplied by this angle. So this arc length you can calculate from the formula like r times this angle in radian. So you have the radius r plus dr and you know the angle, you will be able to calculate this arc length. So circulation is nothing, just the tangential component multiplied by the distance. So here distance is BC, so this distance is r plus dr times d theta would be distance BC. Similarly in CD there is no velocity there. Whatever the length CD, if you multiply by 0, it is going to be 0. And then you have velocity in this dA direction, which is in the tangential direction. So v theta times, and this arc length AD would be r times d theta. So in this way you will be able to calculate circulation of this element ABCD. Okay, if you just multiply these, and because dv theta is a small number, dr is a small number, d theta is a small number. So all these smalls multiplied together can be ignored. So what I do is, if I ignore the third order of small quantities, then I end up with this expression. And from the knowledge of the product rule, if you look at the derivatives, so this thing would be your circulation for supposed to be 0 if it is an irrotational flow. So the circulation is 0 for this element. If it is irrotational, it would be 0, and the whole product is 0. As you know, the whole product is 0, but since d theta is never 0, there is some d theta, it means the term in the bracket is always 0. So I can write, if you multiply, take a product rule, v derivative of u plus u derivative of v, you are going to get the same expression. So derivative of something is 0, it means whatever is something in the bracket would be some constant. So rv theta is a constant, or we have a relationship between the tangential component which would be inversely proportional to r. So as r increases, velocity decreases. So as r is increasing, you are away from the center of the tornado, your magnitude of the velocity is decreasing. As you are coming close to the center of the tornado, your velocity is increasing. So this would be the behavior of that vortex flow. The tangential component of the velocity would be inversely proportional to r. As you know, when r approaches 0 or r at r0, there is velocity would be very large, or we call it, it is not actually defined at r equal to 0, but as r approaches to 0, close to 0, the magnitude of that velocity component would be much bigger. So we have say that point when r is 0, that point is called as singular point, because at that point we cannot define the magnitude of the velocity. And your tangential speed is inversely proportional to the radius. As we already know, vortex flows, such flows having only a tangential component, the radial component is 0, and the magnitude of the tangential component is inversely proportional to r. So as you are going close to the tornado, the magnitude is increasing. As you are going away from the tornado, the magnitude of the tangential component is decreasing. So you have some decreasing function of tangential component velocity, which is some function of radius. Okay, as we have a knowledge of irrotational flow, that the circulation vorticity to be 0 or curl of the velocity to be 0, but the things would be different if your singularity, or the point where you cannot define velocity, is something enclosed in the closed curve where you are calculating circulation. So generally speaking, for an irrotational flow, circulation is 0. But it is not 0, it is only case in which the circulation is not 0 whenever a singular point is enclosed within the closed contour. So let's see, you have, let's say when r is 0, you have a singular point, and my closed contour is like this circle. So what I'm doing is I'm trying to calculate the circulation in this closed contour, which is a circle. So the magnitude of the velocity is the tangential velocity here, and corresponding stream function is, let's say, psi. And we know we are calculating in an anti-clockwise direction. So circulation would be nothing. The tangential component of the velocity, if the line integral over the closed path would be your circulation. So as you know, the magnitude of the velocity at a given radius r remains the same. So for this stream function, for this streamline, this closed path is just the circumference. So if you evaluate this integral, you are going to get the circumference of the circle, because you have differential lengths, and all these differential lengths, if you take the sum, you are going to get the circumference of a circle. So your circulation in that case would be b theta times 2 pi r, and we have seen here that the circulation is not zero in such a case when your closed contour is containing this singular point. So singular point is this. Okay, so you can work out the expression for tangential component, and which is exactly the same as what we have earlier case. We have just a relationship between tangential component. We don't know the value of the constant, but now we know the value of the constant as well, because this circulation divided by 2 pi would be r times v theta, and v theta would be constant divided by r. So here constant would be this circulation divided by 2 pi. So I just make this thing to be constant. So we can say that the circulation around the streamline for this vertex flow in a special case when singular point is enclosed in that closed contour, because closed contour is this circle. So if the singular point is included in that circle, the circulation will never be zero. So in that case, we have some circulation there, and that would be constant. So for irrotational flow, circulation is generally zero. We will see another case in which, so we can say we have an expression for tangential component of the velocity, which is nothing, the circulation divided by 2 pi r. Okay, if you just look at the other case in which you are trying to calculate circulation when your closed path is such that which does not contain singular point. So it is something outside the singular point. Here streamlines are in the tangential direction. We call tangential velocities v1 at a radius r1, and we call it tangential velocity v2 at a radius r2, and we are trying to calculate circulation. So velocity in the AB direction is 0 here, and in the BC direction it is v2, and this length BC is whatever this r2 times this angle alpha. And similarly, the velocity in the CD is 0, so circulation would be 0 times the length CD, and this would be minus just because we are calculating anti-clockwise the circulation to be positive. So and you see from the expression v1 r1 is same as v2 r2. So in this case we have worked out that the circulation is 0. So this is a general case in which we have a closed contour outside. Closed contour is such that it does not have any singular point. So circulation is 0 always whenever you don't have any singularity in your closed contour. So if there is a singularity in a closed contour, then your circulation will not be 0. So this is for irrotational flow, in terms of curl of the velocity, we can simply say the curl of the velocity is 0 or the verticity is 0. That would be irrotational flow. But circulation idea is a little more complicated, because circulation is generally 0 in a closed contour whenever there is no singularity. But once there is a singularity, then circulation will not be 0. Okay, so that is, we can easily work out the expression for the stream functions just like the same we have done for uniform flow and source flow. So for free vertex flows where it is irrotational, then your only acting component is the tangential component, and which is circulation divided by 2 pi r. We have already worked out, and the radial component is 0. So as I know that dava psi by dava r is minus v theta, so I just substituted minus v theta, and then I can separate the variables to get my corresponding stream function in a similar manner. If we have knowledge of relationship between tangential and radial component in terms of velocity potential function, so if I just substitute using that expression, just substitute v theta equal to circulation divided by 2 pi r, I am going to get the expression for velocity potential function, and it would be just opposite to the source and sink flow, because now my stream function is some function of r. So at every r I have some new value of psi. Similarly, velocity potential function would be the radial line. For every theta you would have some value of phi 1, phi 2 and phi 3, so on. So this would be its flow net, which is representing stream function as well as velocity potential function. So in radial flow, the stream function is in the radial direction. In vertex flows, the stream function is in the concentric circles. Okay, the last thing is rotational flow in force vertex flow. So as you know, force vertex flows, so it means it is such a situation when your fluid particles act as a solid body, as you have already seen in your FM1 course. Okay, we see the corresponding stream functions, and for force vertex flow, just work out the magnitude of the velocity is not inversely proportional to r, but it is directly proportional to r. So when angular speed is constant, so this is, you have seen in your physics problems, your tangential component can be worked out if you have a knowledge of r and angular speed, r times omega. So as you, that is something opposite to free vertex flow. In free vertex flow, velocity component was inversely proportional to r. In force vertex flow, velocity component is directly proportional to r. So just let's say you have a disk, and if you are rotating the disk, and if you put some particles at the edges, so their radius is much bigger, so their velocity is much higher. So as you are going close to the origin or center of rotation, your magnitude of velocity is decreasing. So that is the behavior for the force vertex flow. Okay, so what I see here, the corresponding stream function I can easily work out. I just substituted here this expression for tangential velocity, which is r times omega, and you see it is different from free vertex. Free vertex, the tangential component was inversely proportional to r. Here it is directly proportional to r. So as r increases linearly, your tangential velocity increases. So we cannot say like a tornado, it is like a disk which is moving as a solid. So when your fluid particles are moving as a solid, it behaves in a manner, we call it a force vertex flow. Okay, the question is, we have just integrating it, you will be able to work out its corresponding stream function. The question is, can you work out the velocity potential function as you have done it for uniform flow and source and sink flow? You have worked for free vertex flow, but what about for force vertex? The answer is you cannot, because it's a force vertex, it's not a free vertex, because velocity potential function idea only works for irrotational flow cases. So you cannot work out velocity potential function for force vertex flows, because it is actually not a irrotational flow, and velocity potential functions only exist for irrotational flows. And you can think of, compare the force vertex and the free vertex like this. In force vertex, tangential velocity is directly proportional to r to radius. So here it is a rotation takes place, so the particles are actually rotating as a solid body. So, but in irrotational flow, just like a Ferris wheel, if your particle is just like your box and it remains vertical. So where only thing is, as you are going close to the center, your tangential speed is increasing. As you are going away from the center, your tangential speed is decreasing. So that's why you see these Ferris wheels have bigger radius, because human being cannot experience very high velocities. So because if your radius is smaller, then you may experience very high velocities. So that's why the Ferris wheel is always, and is an example of an irrotational flow. So here we are able to finish our today's lecture.